Today I'd like to look at three different problems that come from a couple different introductory mechanics course textbooks that involve projectile motion that we've been looking at in the last lecture, two-dimensional, level ground, no drag or anything like that. One of them comes from Morin's classic Introduction to Classical Mechanics textbook. This is problem 3.39, which asks us, at what angle theta should we launch our projectile so that the maximum range of the projectile is equal to the maximum height of the projectile? The second question comes from Klepner and Kolenkow. This is another introductory mechanics textbook. This is the one I used when I was an undergraduate at Berkeley. This is problem 1.27, which is asking what theta and what minimum launch speed should we send a projectile so that it just barely clears a particular roof, a roof that has a 90-degree apex. And then finally, we'll look at a problem from Tipler and Mosca's more generic lower division physics textbook. This is problem 3.97, which asks us, what is the relationship between the launch angle theta and the angle of elevation of the apex? I'll draw a diagram for that. Okay, let's go ahead and start with this first problem. Okay, recall from last time that we had a couple relations that had been derived for this generic two-dimensional projectile motion behavior. We actually derived what the maximum range of our projectile was in terms of the launch speed and the launch angle, and of course g, our acceleration due to gravity. So recall that that's the range I'm calling r is v naught squared over g times sine 2 theta. So that's a double angle in the argument of the sine. And we showed that that actually has a maximal range when theta was 45 degrees, kind of what you would expect. We also derived this expression for the maximum height of the apex or vertex of the parabola. Still v naught squared over g, except now there's a 2g, and it's a sine squared function instead of a sine of double theta. If we'd already derived those, then actually this first problem is quite simple. If I want to find the angle that sets these two values equal, well, I'll just go ahead and set those two values equal. Now notice that the common values of v naught squared and g cancel from both sides of this equation. I can't cancel the signs though, because one's a sine squared and one's a sine 2 theta. So I should probably re-expand out this sine 2 theta using my double angle identity. So recall that sine 2 theta is just 2 times sine times cosine. Over here, I've left the 1/2. Don't forget that was in the denominator there. Now looking at both sides, I see I can divide out a sine theta. Technically, we should worry about that. Maybe theta equals 0 or theta equals pi would also give a solution. And indeed it does. If you shoot it at exactly theta equals 0, h and r are both 0. It hits the ground instantly after going nowhere. And if I shoot it directly backwards, h and r are also 0 because it goes nowhere backwards. So I can go ahead and cancel out the sine theta from both sides. That does leave a sine theta on this side, and it does leave a cosine theta on this side. Now I just need to figure out what this theta is. The easiest way to do this is to divide both sides by cosine, and I'll also move this 2 over here. When I divide sine by cosine, I get tangent. On the other side, 2 times 2 gives me 4, and the cosine has been moved over. So now it's a very simple equation, tan theta equals 4. Now unfortunately, solving this is not trivial. I don't believe there's any simple expression for what the theta should be, but we can go ahead and take the arctangent to get that theta is the arctangent of 4. And if we plug that into a calculator, we get a value, I have to go remind myself, is about 75.96 degrees. And that tells us that if you launch it at around 76 degrees, the height that it travels and the distance that it travels will be the same. Okay, so that gives us our first solution. For our second problem, here is a particular peak of a roof, and we're told that this roof happens to be a 90-degree angle. Our goal is to launch our projectile from some portion of the roof, maybe the bottom of the roof, and we want to launch it in such a way that it just barely clears the apex of the roof and lands at the other side. We are given that the height of the roof from our starting location is some little h, but we don't know what this launch angle theta should be, and we don't know what the launch speed v naught should be so that it actually just barely clears over the roof. Now notice that from geometry here, I have a right triangle that makes up the roof itself with this horizontal line, and it's an isosceles right triangle since everything is symmetric here. That means that when I drop this altitude, it bisects this triangle, and each of these sides will also have a distance h. After all, these are both 45 degrees, and this altitude gives me 2 additional isosceles right triangles. So here we're in the situation where my range r is twice my max height, which is a little different from the previous problem. So let's start with writing that. We'll follow the same procedure we did last time. As before, we're going to cancel out the common factors. So v naught squared goes away, the g's go away, and also this 2 and this 1/2 cancel out in the max height formula. Both of these values are equal to little h here. Little h is equal to capital H, and then r would then be 2h. Okay, as before, we're probably going to want to expand out my double angle. The signs cancel like they did before. We're not concerning ourselves with horizontal launches. And then dividing, we get tan theta equals 2. If you want, we could go ahead and once again calculate what theta is. And the inverse tangent of 2 is about 63.4 degrees. But actually, if we weren't asked to find this particular theta, we don't need it. We're asked to find v naught, the minimum launch speeds that it clears this roof. You could indeed use this numerical value, but it's always best not to use numerical values that you yourself derived in the process of solving the problem to solve another part of the problem. So let's go back and just say we found that tan theta equals 2, and I don't want to bring in the messiness of my calculator and do I use radians or degrees, how many significant digits to use. That stuff is pretty tedious. So instead, let's ask the second question, what is the minimum speed, without solving for theta directly. Now we know our answer is going to be in terms of this little h, so I can use either the capital H version or the range version since I still have this relation. Let's go ahead and use capital H. And notice here that I don't need theta itself, I need sine squared of theta. Okay, but all I know is tangent of theta, exactly. So we can use this trick of never solving for theta, but using a little right triangle to figure out what sine and cosine would be in case I needed those. Let's imagine drawing an extra little triangle. It has nothing to do with this triangle at all. So I'm imagining just some extra little right triangle that does have an angle of theta in the lower left, say. And we're told that I know the tangent of theta is equal to the number 2. Let's think about that 2 as a ratio, 2 over 1. And you know that tangent, from our SOHCAHTOA usage, is opposite over adjacent. So it should be opposite of 2 and adjacent of 1. After all, the tangent of that angle is indeed 2 over 1. I could leave it as 4 over 2 or something like that, but let's just reduce it. And now we can use the Pythagorean theorem to find out what the hypotenuse would be. And that would have to be root 5, 2 squared plus 1 squared, square rooted. And now that tells me immediately that sine theta is opposite over hypotenuse. And cosine theta, if we needed it, would be adjacent over hypotenuse. So that's kind of cute. We never actually needed to solve for theta itself if I'm only concerning myself with sines and cosines. This trick comes up quite a lot, so it's convenient to know that if you know one trig function of an angle in terms of some rational number or even an algebraic number, then you kind of know all of the trig functions just by building one of these kind of triangles. Just remember SOHCAHTOA. Now I can plug into my H formula Remember that capital H is the given little h, so I'll switch back to the notation that's given. And now I want to have sine squared of theta. Well, sine theta is 2 over root 5, and sine squared will just be the square of that. If I now solve this for v naught, we notice there's a little bit of simplification. The root 5 squared becomes a 5. The 2 and the 4 partially cancel. I can move the g's around, and then I can do my square root. At the end of the day, I'll end up with root 5 gh over 2. This is the minimum speed necessary to just barely clear this roof, and it's launched at this particular angle. Okay, that's our second problem. Let's go ahead and try the third one. In this last problem, let's go back to a generic projectile trajectory. And the question is, how can I relate the launch angle theta, which is the angle that is tangent to this parabola at its initial launch point, to the angle of elevation phi? This angle is the angle measured from the origin to the apex along a straight line of sight. In other words, if you were just measuring out to the place the projectile reaches its maximum height, what is that angle? And what's the relation between those two angles? So that's our goal here. Okay, notice that we have this little dotted green triangle, which has an opposite side of capital H. And by symmetry, the near side is half of the range. So I can immediately write down a relation for this angle phi in terms of the tangent. Okay, that makes sense. Opposite over adjacent is always a good friend here, and that is indeed that little foot angle there. How do I bring in the other theta? Well, we have formulas for h and r as we've been using this entire time. So let's just substitute those in and see what happens. Okay, we can see that a lot of stuff cancels out. The v naught squareds cancel, the g's cancel. Don't forget that extra little 1/2 that's hiding in there. We probably want to once again expand out the sine 2 theta using the double angle formula. Again, we'll see that there's some cancellation. We can get rid of one of the sine thetas. 0 over 0 is uninteresting to us anyway in this case. And we end up with 1/2 divided by 2 is 1/4. And I just realized this r over 2 should have had an extra factor of 2 also. Okay, so now those 2's also cancel out. And we end up with 1/2 tan theta. In other words, the tangent of this angle phi is half the tangent of the angle theta. And if we were given one or the other, we could then invert this to solve for the missing angle. Okay, that's our last problem. And we've looked at a couple different examples of using the range and max height formulas to answer some symmetry questions about generic projectile motion.